welcome back. This is Chapter 7. We're on climate and terrestrial biodiversity. You're doing part of this lecture this week, and I'm doing part of this lecture this week. I'm posting it up the week before spring break, but most of this stuff is not due until the week after spring break. Please be aware that the time continues to pass, so you still need to work on your lab too and make at least one observation during the week of spring break. Let me know if that's really impossible, but you have to take a picture of the light and dark side and submit something with a little bit of your observations. That's because succession is happening in your jar. You also should have started lab 3. Please take a look at it. It has a little bit of setup and takes some time. You have to mold something out of clay. You have to have some ice cubes that you prepare in different colors. One of the challenges of an online class is you are choosing when to regulate your time. I think people are starting to have time choosing when to do things, which is always the challenge of an online class. But please reach out to me if you're struggling with it. Things are getting turned in later and later and later and later, which I get. But at some point it's going to be so late we're going to lap around until the fall semester, and I don't want that. Today I want to talk about climate and weather. And then in the second video, I'm going to talk about ways that we move climate and weather around the planet. The discussion due this week is about biomes. You've been assigned randomly a biome where you need to research it a little bit and then talk about it in your text. You need to read everyone's biome because those biomes are going to be on the exam. There are going to be quiz questions on the biomes in a future week. So please use those like you were taking notes. And I'm going to start. There's some grassland in this picture, and there's some elephants. This is the African savanna. Why is this not forest? Besides the elephants. But why is this land not forested and the rainforest of Brazil is covered in trees? What makes the difference there? And because this is a different biome than the rainforest. The grasslands and the rainforest and the terrestrial forest, we're going to talk about the temperate forest versus the rainforest versus the African savanna versus the temperate or cold weather savannas. We're going to talk all about those over the next couple weeks, but what actually makes those biomes, those large areas, characterized by, basically having their climate being something unique or at least special to that region and the plants and animals that live there? Why? What we have is a discussion today about climate, and climate really determines the kinds of animals and plants that can live in a region. Climate is not weather. Weather is what is happening right now outside. Climate is what the prevailing conditions have been for at least 30 years, maybe 20,000 years. They're how those temperature and rainfall and wind have been consistent or inconsistent throughout the last several decades. Weather is what's happening right now. Today the weather is a little bit warmer than it's been. In fact, it's nearly 65 degrees outside. So as soon as I video this, I'm going to go outside and take a nap because that's how I roll. But your mileage may vary. And then next week during spring break, I'm going to spend a bunch of time outside because the weather is going to be pleasant. Our climate, we have a temperate climate here in New Jersey where I can kind of predict that the summer is going to be pretty hot. The spring and fall are going to be mild, and the winter is normally kind of not as wet and not as cold as it has been recently. And I also want to talk about that in this lecture. Weather is the conditions in the lower atmosphere, so where we live, in an area over a period of hours to days. Is it raining? Is it hot? Is it cold? It's questions about temperature and precipitation. Precipitation is rain. Weather is affected by moving masses of hot and cold air. And that causes different pressure changes in the atmosphere and shifting of the winds. And I want you to be aware of it as we go into spring now, where today, for me filming this is the first day of daylight savings time. So I feel like we're really going into spring. As that has happened, we're getting a shift in the wind, and I want you to look for that. The winds will pick up as the sun is, and we'll talk about today, the way that the sun is warming the earth from our northern hemisphere is getting a little bit warmer. We're getting a little bit longer sunlight days. And one of the things that happens is because of the difference in cold and hot air on those spring and also in the fall days, the wind picks up. And as that wind pick up, we can actually see the effect of the hot and cold air moving through our system here. A weather front, like when they're talking about a thunderstorm front or a cold front coming through, is where I have two different kinds of air masses and they have different temperatures. When you have molecules at different temperatures, they have different densities. Cold molecules tend to snuggle together, their densities increase. Warm molecules tend to spread apart from each other. The density of that set of molecules increases. The density is how close they are packed together. A warm front is when warm air comes in. Because warm air rises, it is less dense than cold air. The warm front air advances over and it goes over the top of the colder air. And we'll see a whole bunch of different clouds, and those swirls of clouds place up above the sky. We're going to look at clouds after spring break. I'm going to have you do some cloud monitoring. We're going to see this spring, I think, a lot of warm front kinds of clouds coming in. Compare that to, and I've changed the words, compare that when we'll see the advance of a cold front. Cold air is more dense than hot air. As the cold air comes in, it sinks below the warm air that has been sitting in our region. This causes the cold air to come in. The warm air shoots up to the top, and it creates clouds that look like anvils. We call them thunderheads, and maybe it even cause a couple thunderstorms. If you've been sitting outside on a summer day, you can feel if there's a thunderstorm coming. Your hairs on your arms will get all kind of standy up, but you can also feel that, I don't know, I get like a shiver when it's starting to come in. What that is you're feeling the pressure differentiation in the air where the cold air mass is coming in. It's getting denser, the atmospheric pressure is increasing, and it's throwing the warm air up, and the storm is on its way. Atmospheric pressure is caused by molecules in the air bumping up against each other. It's greater closer to the earth than as we go up high because the air actually has mass, and all of that air pushing down on us is actually pushing down with pressure. You can feel this if you go climb somewhere at altitude. Head up to the mountains nowhere in New Jersey does this work. So the mountains in Colorado, you go up to 10,000 or 14,000 feet. You go up to Kilimanjaro or the Himalayas. You can feel that the air is less dense because it gets harder and harder with each breath to draw in enough oxygen molecules to get the oxygen you need. You can also feel that pressure on your body. As you climb away from the earth, you can feel the atmospheric pressure change. This is also why you can't open the windows on an airplane. Like, you physically can't open them, but also you shouldn't open them because the air pressure differential between inside and outside the plane is so great that all the air will rush out of the plane. Here, a high pressure air mass. When we talk about a high pressure air system coming in, cool, dense air comes in, it slowly descends, and it leads to a dry weather front. We actually are having right now, we're having a low pressure air mass that's coming in. It's bringing warm air in from the south. The air is rising. As it rises up higher and higher, it gets further away from where it's warm. It starts to cool as it leaves the lower part of the atmosphere, and then it condenses. As it reaches where the clouds are, it gets close together. If there's little particles up there, it'll form, the molecules of water will form around the particles in the atmosphere, and that will lead to precipitation. A low pressure front leads to rain. A high pressure front leads to dry weather. I don't know. The next time you watch the weather, look at it online, take a look at it and see what they're predicting front-wise versus atmospheric pressure. I want to talk about El Nino and La Nina this year too. I have a little bit of introduction to them, but then also what's happening right now as far as I know. I also gave you some links as we go forward so you can keep looking. because it's the weather we're talking about, this varies from day to day. So I can't tell you what the weather is like right now in the future for you, where you're in my future watching this video, but I can tell you how to look at it. El Nino is a thing we talk about a lot this time of year. El Nino is a Pacific Ocean phenomenon, where as the Pacific Ocean warms up, if it is getting a lot of warm air from the equator region, it pushes our jet stream in North America north. And I'm going to show you this from the North American point of view, and then I'm going to expand this out to the world, because the El Nino, La Nina oscillation affects the weather all over the world. When we have an El Nino year, it means the Pacific is very warm. The jet stream, the stream of air that goes across the U.S., moves and becomes a little bit drier and a little bit, it brings a lot of moist air into the southern part of the United States, and into the northern part of the United States and into Canada, it brings a lot of dry, warm air. We associate it here in New Jersey, the El Nino years, with having a really dry, hot summer. In the Gulf Coast and southeast parts of the United States and into Mexico, it's associated with more rain and a higher amount of flooding chances. La Nina is the opposite of El Nino. La Nina is when the trade winds are pushing the warm water to Asia, and I have this in an animation here as well. The trade winds move, I've got a pen, this way. And that takes the warm water that would be coming from the equator and it pushes it all the way to Asia. That leaves this coast of the US and Canada colder than expected. This cold water pushes the jet stream very far north. When the jet stream is very far north, it keeps it very cold up in northern Canada, but it causes our summers to be warm and drier than expected. It causes the Southwest to be dry, and it causes heavy rain in the Pacific Northwest. This condition, though, as much as it's kind of a misery for us, is perfect for Pacific sea life. If you're interested in salmon or whales off of the Pacific coast, that was supposed to be a whale. It's not a very good whale. Not very good at whales. Off of the Pacific coast, this is sort of ideal. La Nina conditions are ideal conditions for breeding in larger populations to thrive. The El Nino Southern Oscillations here is where we watch the patterns of the El Nino, La Nina, and in between years change the weather worldwide. Those periodic changes in the wind patterns and the trade winds in the Pacific Ocean affect the temperature of the Pacific Ocean as it reaches the continent of North America and Asia. This causes changes in the amount of rain and the temperatures that we experience worldwide. So 2/3 of the world is actually affected by if it's an El Nino or a La Nina year. Here, this article here, and I'll leave it, I'll actually link it as a clickable link in your module. This talks about a little bit outside the scope of our class, and it's quite a clickable long page. It talks about the consequences of the Southern Oscillation between Europe, North America, Asia, and even into Australia, and the consequences of that. And it's written for everyday people to read it. We are, as of February, NOAA thinks that we are shifting into an El Nino pattern in the U.S. this year. This is kind of, I made these slides and now I'm watching it happen. It's interesting how good their predictions are. They're predicting that early March, we're going to see a dramatic weather change from the really, really cold weather we were having in January and February to a sudden shift to much warmer days. It's 70 degrees right now. I'm looking at my phone. I'm watching it, hoping I get outside in warmer weather. The last time I made a video for you, so a week ago, it was in the 30s. And you know this winter has been brutal. We expect this weather change to mean that the U.S. is going to be quite warm in much of the continental U.S. We'll have a higher chance of flooding in the Southwest, but the summer should be lovely in Europe, and we'll have a much cooler than average summer in Europe. I want to show you this. This is our predictions from NOAA. So this was issued in January of 2026. This is the most recent data I can give. And so if you pause here, you can take a little bit of time to look at it. What these are saying is this is December, January, February, January, February, March, February, March, April. So this is a seasonal breakdown of 3 months at a time, but it's overlapping of the prediction of whether we're having La Nina or neutral or El Nino oscillations. And here is the clickable link for the detailed article. Here, this is much more recent. I think this was just at the end of February or beginning of February. So you could see, oh, I see what I did. This is the beginning of February. It was freezing cold this winter, much colder on average than we've had in many years. I think it was one of the coldest winters in my lifetime, according to the data, not just my gut feeling. We had this cold weather that sat, there's New Jersey, it sat on us since December, really. As the El Nino takes a hold, these are the predictions as of the end of February. These are the predictions for where we're going. You can see it's starting to warm up across the entire east coast of the U.S. We're going to have a cell sitting in northern Canada. This is Greenland. This is Spain and Portugal right here. So we're kind of looking down on the poles of the Earth. As we do this, this area is going to be much, much hotter than expected. This area is going to be a little bit warmer than expected. You can also look at live weather patterns across the world. This is a fascinating site. I'll also link it in the module. But if you click here, it shows you right now what the wind patterns on Earth are actually doing. I suggest you go back and forth over the next couple weeks and take a look at your planet. It was at 10:46 this morning. You can look at the wind across the Earth. You can, when you're in this site, you can rotate the Earth around and take a look at how the winds are actually blowing. You see we have a little bit of wind. You can see this circle of wind blowing here. You can see the wind patterns, and then the trade winds, these winds here, are starting to pick up. These are trade winds here all the way across. I think they're called trade winds because they blew the ships from one continent to the other for the trades. I also want to talk about hurricanes, tornadoes. They're actually the result of warm and cold air coming together. They are dramatic weather systems that come in when two very different temperature airs crash into each other. Warm, moist air is drawn down. Warm air here is drawn. This area was warm. It's crashing into cold air, which is descending down. And this creates two fronts that slap into each other. They're swirling against each other, and they create a spin. This can be really minor. You could actually see it a little bit on this page here. You can see this isn't a storm. This is just the winds crashing into each other. When it happens over land, we call it a tornado. When it happens over water, we call it a cyclone or a hurricane. And then it brings in really dramatic storm energy. I'm going to show you a tropical cyclone here. The same thing. Warm air cycles in. Cold air is cycling the other way, and they crash into each other and create this. It's a diffusion of energy that is getting rid of the contrast between the hot and cold air, or the warm and cold air. So very short, a little bit about the weather. I'd love for you to check out those sites. We have a little bit of discussion in our discussion this week about weather in the biomes, but enough so that we can drag this through the rest of the semester. This is kind of building onto ideas that we're heading into. In the next video, I'm going to talk a little bit about things like climate, but we leave climate change until mid-April when we're actually talking about the consequences of human impact. I'll just highlight a little bit about that. I'll see you in the next video. And please ask me if you have any questions. All right, I'll see you soon. Bye-bye.